discretization of continuous time systems is very important and common in actual control practices. There are two ways to do this, or there are two categories to do discretization. One is obviously transfer functions. We have continuous time transfer function. We wanted to obtain the discrete time transfer function. Another is, instead of transfer function, we do state space analysis, derive the state space discretized systems. Here, we're doing the transfer function analysis. The state space analysis has already been recorded and is available on the course website. Let's take a look at the big picture. It goes as follows. If we just have a continuous time system, then we will be only looking at this part. We have an input u that goes into some system with representation in Laplace domain transfer function of g of s. Output is y of t. But in practice, we have digital signal processors that generates discrete time sequences. Let's call it u bracket k. And it will look something like this. It happens as discrete time instances, and the index k is just integers. It goes through a holding mechanism that will translate this discrete time sequence into a continuous time function, a continuous time signal. What we care about in here is something called zero-order hold. It holds a signal in this way, just holds it flat between the sampling instances. So for the signal on the left, it may look something like this after the zero-order hold. This signal now is in continuous time. It has values for all time t, not necessarily time indexes, integer time k equal to 1, 2, 3, etc. The zero-order hold has a parameter over here, the sampling time. It's going to hold the signal between the two samples, and then the difference between k equal to 1 and k equal to 0 is called delta t. This is the sampling time between the two sampling points. This continuous time signal goes through the system and it generates some output, y of t. Let's say it may have some shape like this. Then the sampler, y bracket k, will sample from the signal. Again, at discrete time instances, every delta t. That's the spirit over here. And in the end, it looks like something like this, let's say, for example. It has values, it's a discrete time signal, it has values only at time index k equal to 0, 1, integer values, etc. The focus is to derive, on top of this continuous time transfer function, the zero-order hold, the sampler over here. What we want to derive is from here to all the way to here. This is a discrete time system. The input is a discrete time signal, u bracket k. The output is a discrete time signal as well, y bracket k. Now, the step to obtain this is actually not difficult. Imagine if we have a continuous time transfer function. If we apply an impulse to this function and we obtain an output, in the Laplace domain, the impulse function has a Laplace transform 1, and the output has Laplace transform y of s. So in the Laplace domain, y of s equals g of s times 1. If you apply impulse, then the Laplace transform of the output is the transfer function itself. That's for the continuous time system. For discrete time system, it's the same thing. We apply an impulse, which looks like this. it has value just at time k equal to 0. Magnitude is 1. Then we can obtain the z transform of the output, which will equal to g of z. That's the central principle over here. So we can just design the input. We select u of k to be an impulse in discrete time, a unit impulse. And take a look at what the output will look like. Then essentially, we will be able to derive the transfer function. That is the overall picture. Pretty straightforward. The details, actually, there are two little excitements or unexpected surprises that will come out of this derivation. Actually simplifies the result for us. Let's follow our intuition. Let's say uk is a discrete time impulse. Then after the zero order hold, it's going to become something interesting. So impulse is like this. After the zero order hold, you can see it's going to hold the time signal between the two sampling instances. It holds its value, so it's 1 when time t equal to 0, and it's going to hold it until delta t. And then at time equal to t equal to delta t, then we're at here corresponding to the discrete time. The signal has become 0 now, so it's going to hold 0 value for the remainder of the time. This signal is our u of t. It goes into the transfer function g of s as an input and generates an output. This signal, you can see, it is actually it is composed of a standard step function minus a delayed step, a step function that's delayed by delta t. Then it's going to generate this u of t function. So if we observe this fact, you can see that the Laplace transform of this signal, after we obtain the Laplace transform of u of t, then we will know the Laplace transform of y of t. So we want to know that. We want to know capital U of s. The Laplace transform of a step function is 1 over s. The Laplace transform of a delayed step. Delay in the time domain is nothing but exponential function in the Laplace domain. So this delayed step function is nothing but 1 over s times e negative delta t s. That is a first convenient observation. That's going to give us the Laplace transform of the input u is actually 1 over s minus this term. So it's 1 over s is a common term in the denominator s, numerator 1 minus e negative s delta t. So we have the Laplace transform of u, then the Laplace transform of y will become y of s is going to be equal to gs times this input function in the Laplace domain. All right? And then when sample does this simple thing. Y capital K, this is nothing but after sampling, we are just taking samples of this continuous time system at every delta t times k instance, right? K equal to 0, 1, 2, 3, etc. So we are sampling this signal every delta t. That's going to generate our y of k. Let's do it step by step. Let's take a look at this. If we know the Laplace transform of y, then y of t, little y of t, in the time domain is the inverse Laplace transform of capital Y of S. And because Laplace transform is linear, so we can decompose this into two. Inverse Laplace of G of S divided by S minus inverse Laplace of G of S times E negative S delta T divided by S. Two things. So repeating what we have on here, we have this flow chart of discrete time into continuous time into discrete time. And we also have this signal over here. Let us take a look at this final step, this sampling step. We have two things. Let's call these two signals. Let's call this Y tilde t, and then let's call this Y double tilde t. Let's look at them in one by one. Y tilde of t, it gets sampled by this sampler over here. It gives us Y tilde delta t times k. This is defined as our Y bracket k in the discrete time. And this Y double tilde t is nothing but Y double tilde delta t k as well. However, if you take a look at this similarity between these two Laplace transforms, you can see that what we want, so eventually we want to have Y tilde tilde bracket k. If we take a look at this term over here, it equals GS over S, which is precisely the same as the Laplace transform of Y tilde t times a exponential function, right? If I treat this as Y, so this is Y tilde S. Y tilde t corresponds to capital Y tilde S in the Laplace domain. Y tilde S is GS divided by S, right? We're just looking at the signal slightly differently. We can see that Y double tilde t corresponds to a Laplace transform that equals Y capital Y tilde S times an exponential function. So what does that tell us? It tells us Y double tilde t is Y tilde t. I will do it here first. It's Y tilde t delayed by delta t, right? Exponential function in the Laplace domain is delay in the time domain. So Y double tilde t is actually very much similar to Y tilde t. So therefore, we can have Y double tilde, when we sample at every time delta k, then we just replace t with delta tk minus delta t. And it equals Y tilde k minus 1 delta t. That is becoming very powerful now. That explains what? Y double tilde bracket k equals what? This signal here. So if Y tilde delta tk after sampling becomes Y tilde k, then Y tilde k minus 1 delta t after we sample every delta t becomes Y tilde k minus 1. So because of the mechanism of the sampling over here, it has this very advantageous result that this sampled output actually depends entirely on the property or this quantity y tilde k. The second quantity is a derived result from the first quantity. Let's put them into one slide. We have arrived at our y k is y tilde k minus y tilde k minus 1, where this y tilde k is the sampled signal of y tilde t, which corresponds to the inverse Laplace transform of Gs over S. So that gives us the Z transform of y, which essentially equals to the transfer function Gz, as we discussed, if we set the input to be an impulse. The Z transform of the output will be the Z transform of y tilde k signal minus the Z transform of y tilde k minus 1. It's a summary of Z transform of this minus this. And inside is our analysis just one slide earlier. This is y tilde t, and it's sampled at every delta t instance. If we have Z transform, so let's do the first one. The first one is Z transform of the inside quantity here. And the second one, we can see because this is just a y tilde k delayed by one step, we can use the property, the Z transform of y tilde, if it's a discrete time sequence delayed by one step, then Z transform property gives us this is nothing but Z inverse and then times the Z transform of y tilde k, the property of delay in the discrete time. So writing this term a little bit in more details, we can get this. We have Z inverse over here, and then inside is Z transform of y tilde k, which is inverse Laplace of, again, inverse Laplace of Gs over S sampled at every delta t instance. So then we have the fact. It comes into this final formula for computing the so-called zero-order Hode equivalent discretization of the continuous time transfer function Gs. It is combining the previous two terms, right? Gz is, this term is the same. This term is the same. And we can combine them together, arrive at 1 minus Z inverse times this quantity. That's the final formula. 1 minus Z inverse times the Z transform of an inverse Laplace transform. That depends on transfer function of G, a integral inside, and then sampling at every delta t instance. Let's put this into practice. Let's take a look at a first-order system, A over S plus A. So following the procedure, we need to compute Gz. We need to compute a Z transform, and then we need to do a inverse Laplace transform. Starting with the inverse Laplace transform, GS over S, this is quite easy, is fractional order expansion. We can factor out G of S divided by S into these two terms if it's a GS equals A over S plus A. Then we can very easily know the inverse Laplace transform of this signal. Based on the results, you can see inverse Laplace of 1 over S is a step function. Inverse Laplace of 1 over S plus A, this is the exponential function e negative AT. And then we do the sampling. Sample this continuous time signal at every delta t time instance. If you have a step function, it is sampled into a step function. Nothing changes. You get a sampled step signal over here. If you have an exponential function, you sample it, it becomes a sampled exponential function, decaying. And it becomes e negative ak delta t, essentially replace t with k delta t. This is a discrete time sequence, and we can compute from the table of Z transform. A step in the discrete time domain corresponds to Z over Z minus 1. Exponential function geometric sequence becomes Z over Z minus E negative A delta T. Then we just need to multiply this 1 minus Z inverse to this quantity over here to obtain the zero order Hopf equivalent, which is the results at the bottom over here. Let us put this into MATLAB and just to show you how to compute. So over here, I have coded the continuous time G of S into the command lines over here. A, in this case, I assign it as 1. And then the sampling instance, delta t, I set it as 0.1. Then the zero order Hopf equivalent can be obtained by this command called C to D, continuous time to discrete time. You submit the transfer function GS, and then the sampling time, and then you specify the method of discretization. Then here comes the result. You can see the result on the bottom right over here. We have a first order discrete time system. And then the parameters of the discrete time system based on our calculation should depend on this. If we just use the formula that we obtained, then it should depend on, in the numerator, it should be 1 minus E negative A delta T, which is, after computation, 0.095163, which is exactly the numerator in the C to D calculation. And then the denominator will depend on this coefficient e to the power of negative A delta t, which is 0.90484, and it equals the constant term in the denominator as well. So that is the verification of this formula and one example. Let us spend some time to understand this picture a little bit more. Sometimes it saves just a huge amount of effort if you just follow the procedure and intuitively understand what's happening over here. Sometimes you don't even need to use the formula. So I would like you to spend some time and work with me on this exercise. If my system is simply a delay operator, G of S equals E negative capital Ls, where this L is between 2 delta t and 3 delta t. It just delays the input. Let's take a look at this example together. Normally, we would, if we just ask the computer to do this, the computer might say, I want to apply this formula, and then I want to do an inverse Laplace, and then a Z transform. Right? So, using just the formula, this is what we need to compute. We need to do the inverse Laplace transform of E negative Ls over S. But if we just follow our procedure of analysis, we can see something actually happens very interestingly over here. We let the input to be an impulse. Again, after the zero order hold, it becomes this square, rectangle or square signal, right? And then after you pass this into a delay operation, what will yt become? Yt will become, it's just nothing but this signal delayed by L. So L is lying between 2 delta t and 3 delta t. If you delay, which means shift this signal by L to the right, you will arrive at what? Somewhere here, right? Where this is L. You shift, delay this signal by L, it becomes to here. And then this is yt. This is yt. And then you sample it every time delta k at the time sampling time delta k. What's the output y bracket k? You sample this continuous time signal every delta t. So I sample here, I got 0. I sample here, I got 0. I sample here, I got 1. And then all the future, when I sample, I get 0, right? So therefore, yk is nothing but 0, 0, and then 1 here, and then all the way in the future is always going to be 0. So that is how yk looks like, right? And what's interesting here is that no matter what kind of value L is, as long as L is between 2 delta t and 3 delta t, then your square wave may move around in between here, right? But what you get in the sampled output will be always the same. If you shift this a little bit to the left, a little bit to the right, as long as you don't go beyond this boundary point and this boundary point, you will always only be able to sample, get an output at k equal to 3, and you get 1. So, although this problem actually gives you a symbolic transfer function, but the output is deterministic. It is always, so if you take a look at here now, input is a impulse. The output is an impulse delayed by 3 steps. Then you can see that the transfer function is nothing but z to the power of 3. It's just delay the signal by 3 steps, right? If you apply the z transform to the output over here, the z transform of a delayed signal is z to the power of -3. So this is the final solution. You don't actually have to do inverse Laplace and then z transform. This is direct out of the workflow, analyzing all the signals in between here. So in the MATLAB, I have built a little demonstration and then added a few more things beyond. In the MATLAB, I have assigned my delta t to be 1, and then this L value, I just can change it from any number between 1 and 10. And you can see when L equals 1.2, the result is right over here, right? The result is after the zero order hold, you can see MATLAB gives us z to the power of -2, right? If L is between 1 and 2, it's 2. If L increases to 1.4, it's the same z transform, it's the same discrete time transfer function. I encourage you to go back and take a look at a little bit extended example. Think about what will happen if your transfer function in continuous time is an exponential function times a first order system. We discussed both these two separately. But think about if you combine them together, what will be the discretization looking like? I have coded in this example here. You can do the same. It's very simple. You can visualize directly in MATLAB how the result looks like.